When we think about molecules, we usually picture those static, ball and stick models from chemistry class, right? Well, forget all that. The reality is 1,000 times more dynamic. These things are in constant, frantic motion, living a secret life that's just full of nonstop action.
So let's try to reimagine them for a second. What if molecules were like world-class gymnasts? Just picture these tiny microscopic athletes pulling off unbelievable routines 24/7. And, this isn't just a fun little metaphor. It's actually a really powerful way to understand the very real physics behind how they move. And just like any great gymnast, these molecules have their foundational moves. I mean, all of their complex dances and their intricate vibrations, it all boils down to just two fundamental routines: stretching and bending. Seriously, everything they do falls into one of those two categories.
Okay, so let's get into the specifics of these foundational moves. What's really the difference between a molecular stretch and a molecular bend? Let's break it down. Here's the essential difference. Think of stretching as the ultimate power move. It's a pure test of strength. What it does is it changes the length of the bond, so the actual distance between the atoms. It's like a gymnast holding a powerful strength pose. Bending, on the other hand, is all about agility. It doesn't really change the bond distance, but it changes the angle between the bonds. Think of it more like a graceful, flexible floor routine. So let's start with those power stretches. It turns out, even this one move isn't a one-size-fits-all kind of deal. Our little molecular gymnasts actually have a couple of different routines they perform. So what are we actually talking about here? Well, a stretching vibration is simply any motion that happens right along the line of that chemical bond, which causes the distance between two connected atoms to rhythmically get longer and shorter. And this stretching happens in two key ways. You've got symmetric stretching and you've got asymmetric stretching. Let's break down exactly what that means. Here's a really easy way to picture it. Symmetric stretching is like a perfect two-armed push-up, where the bonds stretch and contract at the exact same time in perfect sync. Asymmetric stretching, that's more like a one-armed push-up. One bond is contracting while the other one extends. So it's the same type of move, but a totally different rhythm.
All right, we've covered the power moves. Now it's time for the second category, the flexibility bends. And this is a true showcase of molecular agility.
Now, if stretching was the simple push-up, then bending is the full-on complex floor routine. In fact, there are 4 distinct types, and each one has its own really unique motion. First up, you have scissoring. This is where the two atoms move toward each other and then away from each other, closing the angle between them. Yeah, pretty much just like the blades of a pair of scissors. Then there's rocking. Here, the atoms swing back and forth together in the same plane, kind of like a rocking chair just gliding smoothly on its runners. Next is wagging. In this one, the atoms move together, up and down, or forward and back, but they're moving out of the plane. The best way to picture it is like a hand waving goodbye. And finally, we have twisting. This is where one atom moves up while the other one moves down, which creates this sort of ringing motion right around the central bond. So you can totally see why we say that bending vibrations are the complex floor routines of the molecular world. It's not just one simple move, it's a whole series of intricate, agile motions that really define a molecule's unique character. But all this brings up a really crucial question. Does all this stretching and bending take the same amount of effort? So let's take a look at the energy behind each of these moves. So think about it. Does a powerful push-up require the same energy as just a gentle bend? Well, in the world of our molecular gymnasts, the answer to that is a definite, resounding no. And the difference is actually huge. Stretching vibrations consistently require way more energy than bending vibrations. It's kind of the difference between doing a heavy power lift and just a light warm-up. And it's not just about the energy cost either. Stretching vibrations also happen at a much higher frequency. That means they're not just more powerful, they're also faster and more frantic. Bending is a lower energy move, and therefore it's a lower frequency, a much slower, more graceful kind of motion. So, the single most important takeaway here is simple. When it comes to energy, stretching is always greater than bending. It's the high-energy, high-frequency power move in the secret life of molecules. And that leaves us with one final thought. Why does any of this actually matter? Well, because by understanding these tiny little movements, by knowing which molecule stretches and which one bends, we can do incredible things. We can identify unknown substances, we can predict chemical reactions, and we can even create new medicines and new materials. It just goes to show you how these smallest, most fundamental dances can help us unlock the biggest secrets of our universe.